Okay. Our last speaker for today is Alexander Braverman, and he will give a talk on Hecke operators for algebraic curves over local non-archimedian.
Okay, thank you very much for the invitation. So I will actually give a board talk, and you will see in a second why I will give a board talk. There will be some formal reason for that, but I actually want to start with, I will spend the first like 2 or 3 minutes showing something on the board, and what I want to show is I collected some very incomplete list of quotes from Joseph that I remember from my graduate school. And now the point is that then I will give some kind of mathematical talk, and unfortunately, this mathematical talk will you will see that I will not be following those advices at all, most of them at least. and actually, this is the talk will be. There will be actually very few theorems in talk. There will be more questions, and actually the reasons, probably the main reason that these questions are unresolved is that is that I didn't follow those advices. and you will actually okay, so let me try to put, unfortunately I only just prepared it now, and so this is something in my handwriting which okay, so number okay, so this, wait, this worked 20 minutes ago and now it's not working. So okay, so you see that advice number 0, I remember that you should always avoid giving talks. Well, this was from the 90s, so there were no computer talks. They should not use transparencies because people who use transparencies always talk too fast. So, so that's why I will actually I will pretend that that's the reason why I will give a board talk. Actually, the main reason that I was too lazy to prepare slides, but well, then here are some advices which I actually didn't follow for the purposes of this talk. And you'll see that this little red crosses mean that exactly that. So the first advice, I remember that you should never start a computation unless you know very well what kind of answer you want to get. And next one is that if you have a question, before you try to answer this question, you need to have some reason why the question makes sense. So, and again, I won't be able to explain to you the reason of why I'm doing what I will be doing. Now, the next very general advice, I think, and I'm still not there, is that in order to do something meaningful in mathematics, you should put yourself in some kind of somnambulistic state.
You quoted to me for at least 2 weeks.
Yes, I actually forgot to write it. Yes, exactly. So I remember that this quote I remember very well when Joseph said it to me. This was in the subway in Paris. Okay, and now actually something a little bit more concrete, which I did try to follow. Yeah. And so here's, I remember that, I think that this was in Joseph's office in Tel Aviv. I think Eitan was also there. So he said that somehow one of the main differences between mathematics of 19th century and mathematics of 20th century, this was still 20th century, because you see, I was Joseph student in the 20th century, not in 21st century, is that, for example, very central notion to mathematics is the notion of a function, which will appear in the talk. And in 19th century, function was some kind of object which, had some values at some points, some numbers and so on. And in 20th century, function became just an element of some appropriate functional space. And of course, the question which you should ask now is, what about the mathematics of 21st century? what is, I mean, this is probably...
It's a categorification of a...
Okay. So here is advice number 5. Is that you should always, whatever you're doing, you should always look for categorical meaning of what you're doing. And so here I will try to actually, okay, on a little bit more serious note, so I will try to try to ask some kind of question. So somehow most of what I will be doing will be somehow completely not categorical, but somehow I think there's room for a categorical question. But again, since I haven't been able to put myself in the appropriate somnambulistic state, I can. Okay, so now I'm going to switch to the board. You study ramified automorphic forms, you can sort of very explicitly you can think about unramified automorphic forms in some very easy geometric way. Namely, so in order to talk about automorphic forms, we need to fix some G, which is going to be, let's say, split reductive group. And so, automorphic form, yes, and so then we can study, we can take G bundles on X, and so in principle, as an object of algebraic geometry, this is just, this is an algebraic stack, but we will be interested in just essentially a set of points, or maybe groupoid of points, because we'll, for some purposes, we'll need to remember automorphisms. And so, we can, let's take just this set, and let V be just the space of all complex valued functions on this thing. And this you can think, well, this you can think of, well, at least in one of the definitions, this will be the space of unramified automorphic forms. And well, you can study various subspaces here. You can, for example, obviously you can study functions, well, let me say with compact support, but again, for here compact support means just let me call it VC. This just means finite support. You can also study L2 functions, which actually, let me skip that. But so what kind of questions do you ask here? So if you study all automorphic forms, not just unramified automorphic forms, this is a representation of the corresponding adelic group. So here, because we took the unramified automorphic forms here, there's no action of the adelic group. But, but instead of the action of the adelic group, here you have the action of the Hecke apparatus. So you have action of Hecke apparatus. So let me remind something about those. So, first of all, let me say that this Hecke apparatus altogether, they form some very big commutative algebra acting. So big commutative algebra acting, well, actually on both of the spaces, on V and VC. And so how do these Hecke apparatus look like? Well, so the easiest ones, and we'll need something slightly more general, is the following. Suppose I take some point, some FQ points on my curve. Then I can consider the corresponding Kx. This is the completed, the corresponding local field at X. And, well, this is just isomorphic to some field of Laurent power series over Fq. Inside I have here the ring of integers, local ring. This is completed local ring of integers. And then the kind of spherical Hecke algebra at X. This is, again, the space of compactly supported functions on G of Kx, mod G of 4x, mod G of 4x, and this is known to be a commutative algebra. Moreover, this commutative algebra, well, there are various ways how we can think about it. So somehow, some sense, the most productive ways to think about it is maybe complexified Grothendieck ring of representations of G check. This is the Langland's dual group. This is the ring with respect to tensor product. And and the point is that this algebra, so elements of this algebra act on this space, and the action is by some kind of correspondences, which, well, I mean, these are, after all, you can see the functions here, so somehow they act by some kind of geometric correspondences. So let me give you somehow easiest example, which I will come back to. Easiest example is, suppose G is GLN, and we take, so here we, for example, can we're supposed to associate the Hecke operator to every irreducible representation, and so reducible representations are classified by highest weights. So here we have the operator, maybe H lambda, where lambda is a dominant weight of this group, which means the dominant co-weight of G, and so I'll take lambda to be omega 1. This is the first fundamental co-weight, so it means that the corresponding representation is the standard representation of GLN, which is also G check in this case. And the operator is the following, so in this case bond G is just the same as rank n vector bundles. And we consider the following correspondence H lambda. So this is correspondence which leaves over bond G times bond G, and it consists of the following data. So we can see the vector bundle the same as locally free sheaf of rank n. So we can see the two locally free sheaves like this, and some kappa, which is a map from E1 to E2, such that the quotient is the skyscraper at X. So it's easy to see that these maps have, the fibers of these maps are non-canonically isomorphic to projective space of dimension n-1. It's kind of standard exercise. I'm mentioning this because somehow this will be useful for some example that I will consider later. Okay, so this is the algebra of Hecke operators. So, and maybe one thing I need to say is that, well, of course, you know, all these guys for different points are isomorphic, but here we only get to find if you just do what I did here, then we only get finitely many copies of this thing acting. But in fact, you can do something more general. You can also take X to be a point in X over FQ bar, and in fact, up to the action of Frobenius, and then can do the same. And a better way to, maybe slightly better way to say this is that if we take some divisor on our curve defined over FQ, which you can think of as an element of some symmetric power of my curve over FQ. So FQ points of the symmetric power, it's not the same thing as symmetric power of FQ points. So can do similar thing. So here we can see the modifications of bundles away from a point. We can also consider modifications of a bundle away from a divisor, as long as the whole divisor is defined up to. So a typical example of an irreducible divisor is that when we take a point over the algebraic closure, take its orbit under the Frobenius, get an irreducible divisor. Okay, and so this is a huge, altogether all these things commute. We get a big community of algebra acting, and so the standard question, and to which there's a standard answer, and is, okay, let me erase this too, is how to, what can you say about eigenvalues? So question, how to describe eigenfunctions and eigenvalues. And the answer, which is essentially, okay, so let me switch now, from C to QL bar. As usual, this doesn't really matter, switch. The standard, well, statement, which is kind of, as a conjecture due to Langlands, as a theorem in this case, it's essentially due to Laforgue, is that at least the eigenvalues, there's some delicate question about multiplicity of eigenvalues, but the eigenvalues themselves correspond to, well, okay, let me write Elatic G-check local systems on X, which you can also think of as representations of the fundamental group of our, well, or actually something which is called the Weyl group of X, which is some close relative of the fundamental group of X, with values in G-check. And there's an explicit formula which I won't write on the board, but if you think about the Hecke algebra in these terms, there's a standard explicit map from right-hand side to left-hand side. But it's a very non-trivial theorem that these are exactly the eigenvalues, so it's non-trivial in both directions, so somehow it's both non-trivial that the local system, that for every local system there is such an eigenfunction, and also that there are no eigenvalues. This is both of these directions are, sorry? No other eigenvalues. So both of these directions are highly non-trivial, but in this context, this is known essentially due to Laforgue. Okay, so this was kind of a review of the standard theory. Now, of course, just a remark that, as I said, this is just the story of unramified automorphic forms, and this is the story of all automorphic forms. So this is this you can think of in the context of representation theory of the corresponding adelic group, and this eigenfunctions, they actually correspond to some very specific irreducible representations of the adelic group. So you can think about it this way. But somehow, for the purposes of this talk, I'm not going to do that. I'm just going to take this space. Yes, and maybe last thing I wanted to say is that so here, this was about eigenfunctions in V, and you can also study eigenfunctions in this compactly supportive functions, and that's if you actually want eigenfunctions to have compact support, most of them actually won't have compact support, but some of them will, and this is equivalent to saying that there's a cuspidal eigenfunctions. And also there's a variant which I mentioned before. You can also study eigenfunctions in L2. So again, in principle, as was mentioned in the beginning, so L2 is some functional space, and elements of L, if you kind of look at the formal definition of L2, of course, elements of L2 do not have values at points. But actually, if it's an eigenfunction, it turns out that it does have values at points, so somehow it actually, it's going to be, every eigenfunction actually makes sense as an element of.
No, but this is a countable set, right? So L2 add functions and countable.
This is also true. But anyhow, so just what I want to say is that there are a little bit more functions, so more functions, more eigenfunctions in L2, so this is kind of discrete automorphic forms. So this corresponds kind of discrete spectrum of Hecke operators, so the point is that in this case there's both discrete and continuous spectrum. So in a situation which we'll start considering in a minute, somehow this part will be simple because at least conjecturally there will be only discrete spectrum. So let me just write that both discrete and continuous spectrum exists. So that means that functions which correspond to eigenvalues in the continuous spectrum, they, as actual functions, they're not elements in L2. Okay, so this is a very classical story, and so now let me switch to the following question. And again, I said that somehow the question we'll be studying will not be, in some sense, following Joseph's advice, so somehow I'm going to now present the question. And I don't have any good reason to study this question. Of course, the story of automorphic forms and, Hecke eigenvalues and so on, somehow it has a deep history, and there were a lot of reasons, for example, from number theoretic reasons, why people wanted to study those. So now I want to switch to some different situation where I cannot really give you a reason why I'm going to ask what I'm going to ask, but it turns out that we can do at least something. Okay, so now let me fix f, so I'm going to switch, slightly change the notation compared to what I had before. So now f will denote a local non-Archimedean field. You can also do Archimedean, and some parts of the story are similar, but I think that, I think that's, well, in my opinion at least, Archimedean, non-Archimedean stories here are essentially different. So I want to talk about the non-Archimedean story. And I'm going to choose f, which is, again, a smooth projective curve over f. And sometimes, for some purposes, I will want to assume that it's defined over OF, over the ring of integers of f. And so here's the question, can you play the same game? Okay, let's try to think whether at least we can make this question more precise. So that we can actually do, but this requires a little bit of work. Now, okay, so first of all, we can take this algebraic stack of G bundles on X. We can take its points over F. Nobody can prevent us from doing that. So can we define some nice space of functions here? Let me slightly postpone this question. This is question number one. Question number two, suppose that the answer to this question is yes. The answer to the question really is yes, but I want to present another problem. Assume that we can do this. Then can we define Hecke operators? Okay, so let me explain somehow what the problem here at least could be. And so remember my example when I considered rank n vector bundles, and I consider this Hecke corresponding to the first fundamental way. Now the point is that here, let me just say that if you go back to question 1, then we'll be able to answer this question, but the difficulty here, some kind of difficulty, will have to do with the fact that this is a stack. If this were known as algebraic variety over F, then we could have taken just the space of, say, locally constant functions with compact support. So I prefer to work with compact support. And then let's pretend that this thing is a variety. And let's think whether we can make sense of this correspondence. Okay, what does it mean that we write that we want the correspondence to act on functions? It means that we take a function here, we pull it back, and then we push it forward. What is push forward? Push forward is integration over the fibers. Now remember that I told you that the fibers here were projective spaces, and now this is everything is over local field. And to integrate over projective space, I need a measure, and projective space does not carry canonical measure. And this is so. This is just, okay, so let me just write the problem. No measure. So it turns out that, again, this problem can be cured. So let me now give you some construction. Let me give you some kind of abstract construction. So construction is the following. So let Y be some, well, nice algebraic stack over F. So for example, okay, so here's an example of a stack which will be nice for these purposes. So assume that Y is the quotient of some Z mod some, let me call it A, where Z is some algebraic variety, and A is a linear algebraic group. So band G is not exactly like that, but it's locally like that, and that's enough for my purposes. So then, and let's also L be some line bundle. And for simplicity, let me assume that it's well, I'll make two assumptions. First assumption that I want to make is that Y of, Z of F maps surjectively to Y of F. So that is actually not an assumption in the following sense, that if I can present my stack like that, I can always find a presentation which satisfies this property. So because, for example, I can always find a presentation when A will be some GLN. And for GLN, this is true by Hilbert's 19th theorem. So I'll assume this, and also for just in order to avoid writing some additional formulas, this is not necessary, but I'll assume that A is unimodular. Again, I can always actually assume that A is GLN, so this is not a serious assumption. So assume that I have a line bundle on Y. That essentially means that it's the same thing as a equivariant line bundle on line bundle, let me call it L tilde on Z. Then what we can do is the following. Let's consider Z of F. Well, yeah, and let's also let's take C, which is some complex number. Then it's, well, I'll leave you as an exercise. You can, every C defines some sheaf of complex vector spaces on Z of F, which I'll call absolute value of L to the power C. This has to do with the fact that C defines a map from, I mean, this is, a line bundle defines me in the F star torsor, and C gives me a map from f star to c star, which is just norm to the power of c. And so I can take here, actually, sorry, let me call it not c but kappa. Let me just, because there'll be another c that I want to use. So then I want to take sections, locally constant sections with compact support of this bundle. This is some vector space which depends on, well, okay, let me manifestly write y here. This is L tilde, sorry. Sorry. And here I want to take co-invariance with respect to A of f. So I will denote this y L kappa. So here's a lemma. This does not depend on presentation. On the presentation. So in other words, whenever I have such a nice algebraic stack and a line bundle of it and some complex number, I can define some kind of erosion of the space of locally constant functions with compact support. Now here, okay, if we go back to this context, so kind of main slogan is that we should work with the following space. We take V, take this stack bund G, take the line bundle, which is just the canonical bundle, and take kappa to be 1/2. In other words, we start the section of the square root of the canonical bundle. So instead of functions, we started this. So this, as here following Joseph's advice, so we're defining some kind of space of functions, not by writing values of those functions, although we will be doing something like that in a moment, but we are we're defining some kind of functional space. Now here is a theorem that we can actually define here the action of Hecke operators. So I will not give you the details. There's nothing complicated going on here. And I will demystify this space a little bit for you a little later. So, okay, so theorem if you want. Not completely trivial, but not nothing difficult here is that for every, again, d, which is a divisor, which is an element of the nth symmetric power of my curve over f, and for every lambda, which is a dominant coweight, there exists, well, explicitly defined by some kind of integration, some operator which I'll call h lambda. So this is an operator from this belongs to endomorphisms of this space. So here, let me go back to this diagram. So let me just explain what happens here. So again, so there was some kind of slightly complicated definition of the space. Let's ignore that. So let's really think about it as some kind of space of functions, or rather not functions, but sections of some line bundle. So what happens here is that I take sections from line bundle, I pull them back to this correspondence, and then I restrict it to the fibers. And then miraculously it happens so that for every fiber, the line bundle I get on the fiber, so I take the corresponding, this, square root of the omega, you can actually call it critical line bundle. So I take this critical line bundle, I pull it back here, and then I restrict it to the fibers of this map, of the other map. And it turns out that this critical line bundle has the property that its restriction to every fiber of the other map is canonically the canonical bundle of the fiber. And so, therefore, I can integrate that. And miraculously, something like that happens for every coweight. And this is actually, and this essentially appears in the work of Bernstein and Greenfeld on quantization of Hitchin Hamiltonians. So, in order to produce those Hecke operators, what you need is this work on Balanced and Dirichlet, and plus you need some argument. So because here, in general, not in this case, but in the more general situation, the integration will be, the fibers of the corresponding map will be non-compact. You will be doing some kind of non-compact integration. You need some argument about why this thing is convergent, but again, there's some algebraic geometric argument which guarantees convergence. So let me not go into that.
What do you mean? Guarantees convergent only for some functions.
No, it guarantees convergence. Well, this is the space on which I'm defining the operators, but somehow the problem, the point, well, again, not in this example, but in more general examples, I will be considering some correspondences with non-compact fibers, and then somehow when I define these correspondences, I need to do some work in order to explain why the integral makes sense. But again, I'm hiding that under the rug. Okay, so conclusion. For every G and for every X, which is again smooth projective curve, over F, in fact, I'll generalize this slightly in a second. Smooth projective curve over F, we defined some vector space. Well, let me just denote it by V of, just not to write too many of these things, just write it V of Gx. Defined V of Gx, some vector space, plus some large, in this case it's really kind of absolutely huge commutative algebra. So the claim is that all these Hecke operators commute, so I didn't write it, but commutative algebra of Hecke operators. So it's the algebra itself, in this case, is kind of much bigger than what it was in the case of finite fields. Because in the case of finite fields, you know, at every point of the curve, you had an algebra which kind of had the basis corresponding to dominant co-weights. Here you have absolutely the same thing, except that I said that what you can do more generally, you can define Hecke operators which sort of live at every divisor defined over F. And you know, typical way to construct a divisor, as I said, is to just take an element, is to take a point of the curve of algebraic closure up to the action of the Galois group. Just take the Galois group orbit of some point over the algebraic closure. And of course, finite field doesn't have, you know, algebraic closure of a finite field. This is a very easy and manageable thing. So here, we're working with a local non-Archimedean field. Its algebraic closure is much bigger than the original field, and so you have a lot of different extensions, and so every point defined over every extension of our field defines such kind of some kind of action of some kind of algebra of Hecke operators. For every such point, it will have the same size as before, but we have much more points than before. So now really can ask a more mathematical question. What can we say about eigenvectors and eigenvalues? Now, I should say that, okay, so let me, first of all, tell you a few conjectures. Well, a few theorems and a few conjectures. So first of all, my space was very abstractly defined. But it turns out that it's not as abstract as you might think. So how much time do I have? 20. I'm supposed to finish at 6, right? Okay. Okay. So no, that's okay. I mean, so let's go back to the definition of my space. So remember that I had this algebraic stack y, which was equal to the quotient of some z mod, I'll call it A. Now let's assume that this quotient is not very bad. Let's assume that generically the action of A on Z is free. This more or less means that generically Y is a scheme and not, or maybe an algebraic space, but let's say, in other words, let's assume that Y has an open subset U, open dense, such that U is a scheme. Then we can, well, I suppose we have this, whatever, what I called VL, we called VYL kappa. So we can try, so here I'll write an arrow, but we can try, and I'll explain what try means in a second. We can try to write a map into gamma just locally constant of this absolute value of L to the power kappa on U of F. And so how can we do it? Okay, so let's really forget about L, let's really think about functions. Just so what are we doing? So we have this action of A on Z, so there's and generic orbit is free. And so actually, even if we do have L, then because it's L is A equivariant, if you have a free orbit, on that free orbit, it will get trivialized. But then let's think about, but actually, just for simplicity, I mean, this was maybe a remark, but for simplicity, let me now assume that L is just trivial. So what can we do? Remember that I assume that A is unimodular. So, therefore, it carries more or less canonical higher measure, well, up to normalization, I can choose this normalization. And then what I can do is that if I have any function, if I have any locally constant function, compactly supported locally constant function, I can try to restrict it to this free orbit and integrate. Right? So this is integration over free orbits. The problem is that I'm not guaranteed at all that the integral is convergent. Although I started with functions with compact support, when I restrict it to the orbit, free orbits are not closed. When I restrict to the free orbits, I don't get a function with compact support. So nobody guaranteed convergence. And so, for example, we can ask the following question. This is a kind of question, and of course, one type of mathematical words which are typically associated with Joseph's name is algebraic analysis. So here's a question on algebraic analysis. So let's, for example, assume that everything is smooth, assume that Y is smooth, and I'll take L to be just the canonical bundle, and then we can ask a very general question in this situation. This is a question essentially about group action on a variety, generically free group action on a variety, for which kappa, if any, is this map well defined. And if it is well defined, what kind? If it is well defined, then what? Even if the integrals themselves make sense, you also have to check that you get some kind of something locally constant here. This is not obvious, and in fact there are examples when integrals converge, but this thing is not locally constant. So for which kappa is this map well defined? This is supposed to be some property. So this is actually a fun question to play with. It's already fun if you consider just action of the multiplicative group on the affine line. And so this is, and it's more fun if you consider, for example, action of PGL2 on configuration on a set of 3 points in projective line. So then find the range of kappa for which this map is well defined. So call such kappa good. And now, just a remark is that it depends in principle on choice of this U. We can, of course, we can try to take the maximal set U, but somehow it might happen that we can choose some smaller set, and then somehow that some kappa will be good for some smaller subset, but not for the maximal possible. So this is relative to U. But if kappa is good relative to U, then at least we can think about our elements of our abstractly defined space as actual functions or maybe sections of some line bundle on some explicit space. Now, here is a theorem. Well, in fact, it's a theorem. I should say that it's a theorem for in rank 1 of PGL2 and conjecture in general. So let's assume that, for example, for simplicity, assume that G is adjoint. Then we'll consider the stack band G. Inside we have this open subset, which is actually a scheme of stable bundles. But that's actually not the U I want to check. I want to choose, surprisingly. So this is open subset. This is a scheme. Inside there's some slightly smaller subset, which is called very stable bundles. And it is defined in the following way. I mean, so formal definition, I think it's originally due to Lamont, maybe. So very stable, so E is very stable if any Higgs field, any phi, which in Higgs field is an element of H naught of the following thing. So I take the vector bundle associated with the adjoint representation. E is a principal G bundle. I'll take the vector bundle associated with adjoint representation. For G lambdas, it's just endomorphisms of my vector bundle. And tensor with omega, omega 1 of the curve. This is called the Higgs field. If any phi like this, which is nilpotent, so nilpotent essentially means that at every point of the curve, you get something like an element of the Lie algebra tensor with some one-dimensional vector space. So somehow it's easy to convince yourself that you can make sense of the word nilpotent here. So for J again, this thing is just an endomorphism of the corresponding vector bundle tensored with omega 1, which is nilpotent is 0. So there are no non-trivial nilpotent Higgs fields. There's a lemma which is non-trivial, not super difficult, but non-trivial, that every very stable bundle is actually stable. Let me skip that, but it's true. And so here is a, well, okay, theorem in quotation marks. This means that it's actually actual theorem, so proved and written for PGL2, conjecture in general. Is that kappa equal to 1/2 is good relative to very stable bundles. So every element of our space is actually a locally constant, well, not function, but it's a locally constant half form on the space of very stable bundles. There's also a conjecture of Kashdan and Polishuk that if you can ask what happens if you actually consider all stable bundles. I will not need this, but that it will say, conjecture says the following, that if we take U to be all stable bundles, then, this is U, then the claim is that this should be a map from, this should be an embedding from our V, well, let me just call it V, into continuous half form, continuous sections of omega to the 1/2. Rather than locally constant. So, for example, typical example of a function which is continuous but not totally constant is the norm. So, or some powers of the norm. So such things appear here. And this conjecture, so the form of the conjecture, this conjecture can be reduced to some very explicit but very complicated statement in algebraic geometry. So I think this is proven maybe for genus 2 and almost proven for genus 3, something like this. But I don't have punctures right now, so I wanted to talk about punctures, but I probably won't have time to talk about punctures. So now here's another. Well, this theorem is okay. So this was quotation because it's actually only a theorem for GL2. Now here's the quasi-theorem. Quasi-theorem means that I think I know the proof, but it's not written. But again, I think I know the proof for PGL2 is that, well, you get some locally constant half forms. Now, half forms, I mean, reason we needed half forms is that only in half forms we had the action of Hecke apparatus, for reasons I tried to explain. Now, half forms are also nice for the following purpose. If you study actual half forms on some algebraic variety, then half forms is exactly the sections of half forms are exactly the things for which you can define the space of L2 functions. Because in general, to write L2, you need a measure on your space. If you don't have a measure, you work with half forms. So, so quasi-theorem is that our space V actually, right, and so here we actually have an embedding of our V into locally constant half forms on very stable bundles. But we don't know, this is locally constant, definitely not with compact support, so something complicated happens when we go to the boundary of the set. So here, for example, according to this conjecture, if we go a little bit to the boundary, just to stable bundles, we get something continuous, but you know, this space is not compact, so somehow, even if we can see the stable bundles in general, well, unless you're, well, in some situations it is compact, but in most cases it is not compact. So, and so the conjecture is that this V actually goes into, well, locally constant, well, Bungie very stable half forms intersection with L2 of, well, let me just write L2, but again, L2 means that this is a known as smooth algebraic variety. There's a half forms. There's a space of L2 half forms. That, in other words, that everything in the image is square integrable. So this is again something which you can ask in general algebraic analysis. Suppose you have a group. Suppose you have a stack, which is generically a scheme. Then you can consider this space corresponding to omega to the 1/2. And then assume that you can. That this 1/2 is a good number in my sense, that in other words, that I can realize elements of my abstract space as actual half forms on this open subset, which is a scheme, then you can ask, are they square integrable? In general, I don't know what is the geometric criterion which guarantees this, I have no idea. But in this case, conjecturally that's the case, and for PGL2 we can actually prove that. Okay, now I don't have too much time left. Now let me, so we do have the setup. So we have this space which we can actually define. We can define Hecke apparatus. We can realize the space as actual half forms somewhere, but we don't know growth conditions, but somehow at least there's some half forms. Now what about the eigenvalues? So here, let me present some very partial results. The problem that, so here's bad news. Bad news that I don't know any eigenvalue which I can describe explicitly. I can describe some eigenfunctions, but I don't know how to describe the corresponding eigenvalues. I partially know how to describe the corresponding eigenvalues. So let me explain. Okay, so examples. No, this is a conjecture. Okay, maybe I should say, actually, this is a conjecture which is actually due to U. So this is, or maybe U with Frankel and Kashdan, is that this Hecke apparatus. So it means that the space is, it has a canonical, the space which we work has a canonical unitary structure, and the claim is that the Hecke operators, it's obvious that the image of the space is dense in L2 because any compactly supported sections are obviously there. It's very easy to see. So completion of this space with respect to this L2 norm is actually all of L2, and so the conjecture is that the Hecke operators are bounded. Yes. Okay. Yes. Compact, which implies that that we only have discrete spectrum. Well, yes. Okay. I didn't say. I didn't say what. Since I didn't say what Hecke operators are, then you're right. But okay, you're right. But compact and some of them, most the ones we can write explicitly are actually self-adjoint. Okay, fine. Okay. Okay, fine. Normal. Okay, fine. Only have discrete spectrum. So this is going to be relevant for what I'm going to say in a second. So examples of eigenfunctions. I will tell you two examples. So one example is the following. Suppose that now, again, my x is actually defined and smooth over the integers. Yeah, everything is projected. So there's a story for non-projective curves as well, but I won't have time to talk about it. So then the claim is that we can define some canonical operator, which I'll know by E. E actually stands for Eisenstein. This is actually some version of Eisenstein series. This is an operator from compactly supported, finitely supported functions on band G of x over FQ. So this FQ is the residue field of this thing. To my space V, which I denoted by, in fact, I can define it for any kappa, but let me concentrate on kappa equal to 1/2, but in fact, this one I can define for any kappa. Okay, let me say, actually, let me say it's defined for any kappa, so let me call it E kappa. This is very easy to define. This I won't go into this, but this is elementary. What is less elementary is again the following quasi-theorem. Quasi-theorem means that it is first of all, it's not written. Second, that I only know the proof for SL2 for PGL2, but don't know proof in general. So first part is actually for any G, and it is easy. This thing maps eigenfunctions to eigenfunctions. But again, something non-trivial happens to eigenvalues, and unfortunately, I can't say. I could say something about that, but I don't have time. Second is the following. So note that at least eigenvalue. If you start with an eigenfunction here, we're going to get some eigenfunction here, and the eigenvalue is supposed to be kind of produced from the eigenvalue here. Now, here, as I said, we have both discrete and continuous spectrum. Here, we only have, at least conjecturally, only discrete spectrum. So what happens here? What happens is that this map is not injective, actually. It actually kills some stuff. And the thing which I can prove for G equal to SL2, for example, is the following, that this of course, this is for kappa equal to 1/2, because only for kappa equal to 1/2 we have Hecke operators. So for G equal to SL2, this E to 1/2 is unitary on the cuspidal part. No, unitary. Well, okay, I don't know. Preserves L2 norm. So, okay, is it called isometry? Okay, if you say so. Is well, okay. Let me say you have preserves L2 norm. So in other words, we are supposed to be able to associate. So here we know how to classify eigenvalues. They correspond to local systems. Cuspidal ones correspond to irreducible local systems. So for every irreducible local system, we're supposed to construct an eigenvalue in this world, but only for reducible ones. So for non-reducible ones, we're not supposed to be able to construct an eigenvalue. I don't know what it means. Let me give you another example of a cuspidal function. Well, I won't describe to you the function, but I will describe for you to which data I can also. So here I can assign a cuspidal eigenfunction to every. I can assign an eigenfunction to every cuspidal eigenfunction in the kind of classical situation. Let me describe another example of input to which I can associate. And it doesn't make sense. So I don't know how to describe the eigenvalues at all. In even for GL2, I mean.
In this case, the second part also eigenvalues are.
No, if you consider eigenvalues, I can describe the eigenvalues which correspond to points defined over F. Eigenvalues which correspond to arbitrary divisors, I have no idea how to describe it. That's. For points defined over F, you can describe, yes, but well, in the appropriate sense, yes, but yes, well. Well, okay, so the claim is that for every, if you choose any divisor, and consider the Hecke algebra which sits in this divisor, there's a homomorphism abstractly defined, which, and I don't know how to write it explicitly, from the Hecke algebra of things which sit in this divisor to the Hecke algebra of which sits in the reduction of this divisor here, such that this map is equivalent under that. The problem is that I can abstractly define as homomorphism of Hecke algebras. I don't know how to write it explicitly.
However, if this divisor consists of one point,
well, okay, this makes no sense because somehow identity map is only a map from the vector space to itself. And if the group is GLN and
identity map for basic representation.
if the group is GLN and divides at one point, then we can describe this map. Yes. But so here's another example. Okay, I have to finish, so let me give another example very quickly. Another data is the following. For simplicity, let me assume that G is, say, SLN, or well, even GLN. Let me assume GLN. Then let's do the following thing. Let me fix an additive character of my finite field, and let me fix also the following thing. Let's consider the cotangent bundle to bund G, to bund GLN. This is called the Hitchin space, and it has something which is called the Hitchin map, which I won't describe for you. So this space consists exactly of pairs E and phi, where phi is the Higgs field as before. And so this map is in general kind of complicated, but generically this map looks nice, and generic fiber here is essentially an abelian variety. More precisely, if I take really JLN, so generic fiber is Picard of some curve, which, well, generic fiber, let me call this A, and so if A is a point here, the generic fiber is Picard of some smooth algebraic curve, which is actually an n-fold cover of our original curve X. Well, generically it's equal to Picard. If the spectral curve is smooth, then it is equal to all of Picard. And so we have this curve is an n-fold cover of X. This is called spectral curve, and then let's call kappa. Let's take kappa to be a character of this thing. Then to this data, one can again attach. There's some construction which I don't have time to explain, but this is just one can attach an eigenfunction. And again, for GLN, I can say what the eigenvalues are for Hecke operators which sit at points, but not for more general divisors. So let me conclude that this was basically a question. As I mentioned already a couple of times, I don't really have a convincing reason why this is a meaningful question, but it kind of looks fun to play with. And maybe the last thing I wanted to say is that remember that in my list of Joseph advices, the very last one was that you should really think about categorical meaning of everything. And I think that the main reason why I don't know how to write a good formula for eigenvalues, even in the cases where I know how to construct some eigenfunctions, is that because we don't really understand what those Hecke operators form. So I think that, in the kind of usual situation, we have the spherical Hecke algebra, but you should think about it something like the Grothendieck group of the corresponding what's called Satake, geometric Satake category. And so here there should be also something like that, but in the usual case, this category, our Hecke algebra is a decategorification of some tensor category. In this case, my expectation is that there should be some kind of category, but this category will be it will be monoidal category maybe, but it won't be a tensor category on the nodes. For example, it won't be symmetric. It will only be symmetric on the level of the Grothendieck group, but not symmetric. And probably it will not be even braided. So it should be somewhat similar to the category of fine-dimensional representations of quantum affine algebra, something like that. I could have elaborated a little bit more on that, but unfortunately I have to stop. So, okay, that's it. Well, okay, so by Fourier coefficients you mean something like the Whittaker model or something. I don't know how to do that, so somehow it's a good question. Things are kind of too infinite. So I'm not saying it's impossible to do, but somehow, you want to write this kind of Whittaker integral, so somehow I don't know how to make sense of that. I'm sorry? What do you mean by periods? I don't know, but I don't know.
Isn't it what is called separation of variables?
I don't think so. Okay, we can discuss this, but I don't think so.